All right, so up at the top of the first page, it says the National Association of Realtors estimates on average that the price of a house doubles every 10 years. So we're talking decades here, right? Decade is every 10 years. So every decade, the house price doubles. Tony's grandparents bought a house in 1960 for $10,000. Assume that the trend identified by the National Association of Realtors applies to Tony's grandparents' house. Okay? So number one says, you can read the questions. Go ahead and answer numbers 1 through 3 together with your partners. Okay? So answer 1 through 3 together with your partners. Go ahead. Okay, so number 1 says, what was the value of Tony's grandparents' house in 1970? So if it was $10,000 in 1960, how much should we assume it's going to be in 1970? It's $20,000, right? Because it doubles. So $20K. I'll just say $20K for $20,000. Okay. Compute the difference. Oh, sorry. We're not done with that problem yet. What about 1980? So this was 1970. And then in 1980, another decade, it should double again to give us 40K, right? All right, so then it wants us to compute the difference from 1960 to 1970. So what was the difference between 1960 and 1970? $10,000, right? So $10,000 is the difference. And then it wants a ratio. So the ratio of 1970 to 1960 would tell me to put 1970 on top. That was 20K, or 20,000. And 1960 on bottom, which was 10,000. So if I reduce 20,000 divided by 10,000, what should my ratio be? 2. Right? 2 over 1 or just 2. So then taking that information and filling in my table here, I'm going to help you kind of get it started here. So it gives us the information for 1960. Obviously, that's 0 decades away. House value is $10,000. Then 1970, how many decades away from 1960 are we then? 1. We're 1 decade away. We figured out the house value was $20,000. We also figured out the difference between 1970 and 1960 was 10,000. And we figured out the ratio of 1970 to 1960 was 2. Right? So let's go ahead and fill in 1980 together. So in 1980, how many decades away are we now? Now we're 2 decades away. What did we figure out the house value should be in 1980? 40. If it continues to double, it should be 40,000. So then I need the difference between 1980 and 1970. What's the difference between 1980 and 1970? Just 20,000, right? The difference between 40,000 and 20,000 is just 20,000. And then my ratio here, so let's go ahead and pull it over and compute again here. So my ratio of 1980 was 40K divided by my 1970, which was 20K. So what's 40,000 divided by 20,000? That's again 2 over 1. So I just have a ratio of 2. Okay. All right. You guys go ahead and together with your partners fill in those bottom 3 rows of the chart. Go ahead. Hopefully your data matches mine. Okay. So looking here, what kind of patterns do you recognize in the table? Yep.
Every time it goes up a year, the amount before that doubles.
Up a decade? So every time it goes up a decade, the amount doubles, which would make sense, right, with the information they've given us. They told us every decade it should double. Anybody notice any other patterns?
The ratio is the same.
The ratio is always the same. Okay, that's something that's going to be really important to us when we are learning about this new type of function. Let me ask you, is the data in our table linear? Everything that we've done in the past has always been linear. Is the data in our table linear? Let's specifically focus, because these are the 2 that they're going to ask us to focus on. The number of decades versus the value of the house. Is this data linear?
No.
Right here? No. How do you know it's not linear? I need 10 people that can tell me why they know this is not linear data. I currently see 4. 5.5. Are you 6 or are you a half? Okay, so I still have 5.5.
They make it even 6.
He made that an even 6. Oh, jeez. Okay, Alexa, how do you know that this is not?
It doesn't have a constant rate of change.
Okay, it doesn't have a constant rate of change. Specifically, if I'm looking over here in my value of the house, if this was linear, I should expect to see 10,000, 20,000. What should I expect to see next? 30,000, 40,000, 50,000, right? If that was going to be a linear, linear data or a linear function, I should expect to see a constant rate of change, my data changing equally every single time. I can see that this is not just changing. So that scenario would be something like the National Association of Realtors notices that every decade the house's value increases by $10,000. That would be linear, right? Because then we would go 10,000, 20,000, 30,000, so on and so forth. Okay, but that is not what this says. It says it doubles every year. So we can see that our data is not linear here. Okay, so we're kind of moving out of that realm of linear functions and now moving into what's called an exponential function. We've been working with exponents. Now we're going to look at functions with exponents in them called exponential functions. Okay, so that being said, go ahead. I'm going to leave mine here so that we have the data up there so you don't have to scroll back and forth. Go ahead and scroll to the next page. I believe we're also going to skip number 6, and number 7 is where it tells you to graph, correct? Mm-hmm. Yeah, okay. So I'll leave my data up here. We're using decades since 1960 as my X value, and we are using the house value as the Y value, okay? So using the table from the data up here, you can go ahead and graph your points. Go ahead. Okay, so hopefully your data or your graph matches mine. Okay, and it tells us in number 8, it says the data comparing numbers of decades since 1960 and the value of the house are not linear. Okay, well, we already figured that out from the table of data. Who can very easily tell me how we know the graph is not linear? Travis?
It doesn't go in a straight line.
Doesn't go in a straight line, right? It's as simple as that. Looking at any graph, if it goes in a straight line, it's linear. If it doesn't, obviously it's nonlinear. We already talked about the table, or the data in the table did not have a constant rate of change, so we knew it wasn't linear from the table as well. I want to take it kind of a step further here, and I want to give you guys about 20 to 30 seconds here to talk about how this changes. Okay? So get specific. Don't just say it's not linear. Talk about specifically how this function changes. Maybe how does it change at the beginning versus how does it change at the end, different things like that. Okay? So I'm going to give you about 30 seconds to kind of discuss that together with your groups. Go ahead. Okay, I heard lots of good things. Can somebody kind of share with me what you guys said? How about my back group back here? What did you guys say?
With each couple of decades, like once you move up the graph more, the gaps get wider.
Okay, so as you kind of move up the graph, the gaps get wider. That's one way of saying it. Yes. Anybody else want to tell me what they said? Well, I heard a lot of people talking about in the beginning. So what happened in the beginning? Starts off kind of slow, right? I mean, obviously $10,000 is a big jump, but in the grand scheme of things, looking at our graph, it's not necessarily growing that quickly down here, right? In the first couple decades. But then as the decades increase, I mean, you can really see it really starts jumping up, like way far up, right? So what if we extended this pattern? What if we, because that's what question number 9 asks us, using the information we found, predict the house value in the year 2020. So the last data point that we put down was 2010. So what should we estimate the value to be in 2020? What? 640? How do you know it's 640? Okay, so the first one, or the data point at 2010 was 320, so we double that. We should get up to 6,000 or 640,000, right? So that being said, what if I asked you, what will the house value be in the year 2160? It's obviously going to be a gigantic number.
Would the house be like 100 years old?
Okay, but my point being, and I think we're kind of missing my point. I obviously this is not a perfect example, but if my point being, if I jump way far out, I need some way of easily figuring that number out without having to take my table and double and double and double and double and double and double and double. Okay, so let's look at what these functions look like. Okay. That's what we did with linear, right? We found some kind of linear pattern, and then in order to extend that linear pattern, we made a function that could tell us input and output values very easily. Let's do the same thing here, okay? So let's go ahead and flip to our last page here. All right, so it says, in exponential growth, a quantity is multiplied by a constant factor. That is huge, okay? And we don't want to get this confused here, because when we did linear, we were multiplying by a constant number, right? Or a constant rate of change. A constant rate of change is very different than a constant factor. Okay? So it says in number 11, the value of Tony's grandparents' house is growing exponentially because it is multiplied by a constant factor for each decade. So what is that constant factor? So talk really quick amongst your groups. What do we have to multiply the current value by every single time to get to the next decade? That's the question you're asking yourself. What is that constant factor? Okay, so I heard everybody say it right off the bat. What did the paragraph tell us? Every decade the value of the house what? Doubled. So what would our constant factor be? 2. So this is an important concept, guys. We have this constant factor of 2 because we are doubling each decade. What if I said the value tripled each decade? What would my constant factor be? 3. If I said the house lost half of its value each year, what would the constant factor be? 0.5, right? Because a negative doesn't necessarily mean you're losing money. That would just take it into a negative value, right? If it was 10,000 and then I multiplied by a -2, that would make it -20,000. And I don't think the house is going to jump that way, right? If it's losing half of its value, I just want to cut it in half each decade. So my constant growth factor would be 1/2. Okay? All right. So that's important for us to remember. So now it gives us this little statement here. A function that can be used to model this house value is h of t equals 10,000 times 2 to the t. Okay, 10,000 times 2 to the t. You know what? I think I skipped something on the last page, on the bottom of the last page. I can't scroll back because of my video, because it'll mess my video up. But scroll down to scroll back up to the very bottom of the previous page, and I'll just highlight the important part. So the important part out of that little box down at the bottom is that it tells you every exponential function is f of x equals a times b to the x power. Okay, that is the important part. We will unpack and look at exactly what that is. So at that box at the bottom of the previous page, go ahead and highlight that little part. F of x equals a times b to the x power, because every single exponential function will look this way. What is special about the form of that function versus any of the rest that we've looked at so far? Travis? Okay, it does have an exponent. We need to be a little more specific than that, because we will look at other functions this semester that have exponents in them, but they won't necessarily be exponential. It has what?
An x for an exponent.
It has an x for an exponent, and that is very, very important. I know we see a, b, and x, but in every exponential function, those a and b values will be numbers, and the x will stay the variable. The important part about an exponential function is that the exponent is a variable. That's where your variable is, okay? So kind of applying that now, looking at hours, right above, in that little sentence right above 12, it gives us this function. It gives us 10,000 times 2 to the t. Okay? And let's unpack what this what all these parts are. Okay? because the parts always stay the same. The A value is always the same thing, the B value is always the same thing, and the T will always be there. T or X or some variable there, okay? So just kind of over to the side, let's unpack this. So where did 10,000 show up in our problem?
Very beginning.
In like our house scenario, what was 10,000? That was the initial value, okay? So that A value, or that number that's always sitting out front of the multiplication, is always the initial value. Okay? And we're not going to write these today, but we will be writing them tomorrow. So we have to know this stuff. So that 10,000 is the initial value. Okay, that's always the initial value. What was this 2? What did we figure out what the 2 was up above?
It doubles.
It's the rate or the factor. You can call it either one of those things. So the rate or the factor. Okay, so if we're doubling, that factor's 2. If we are tripling, the factor's 3. If we're cutting stuff in half every term, the factor is 1/2. Next time when we get into interest rates, we will find that our interest rate becomes that same rate or factor that's in there. Okay, and we'll have some kind of initial investment, we'll have a rate, and we'll have a time. This T is always going to be your time. Okay, so that T is always going to be your time. So kind of break things up here. So we have that A value that's out front, that's my initial. We have that B value that's always my rate or my factor. And then that that variable will always be there in the exponent to be your time. Okay? All right, so let's kind of just look at what we can do with this. Okay? So taking that function, let's graph it. Okay, so taking that function, let's graph it. So it's conveniently right here on 13 for you. Okay, so I want to take that function, and now I want to graph it for t is 0, 1, 2, 3, and 4. The only way that we will graph these in this class, you'll do more of this if you make it to pre-calculus. Okay, you'll do more of this then. But for now, okay, the only way we're going to graph these is with a table of data and then putting our data points on a graph, okay? So the 10,000 is always going to be 10,000. The factor is always going to stay the same factor, but my T is going to change based on the inputs that we're putting in, okay? So use those different T values, plug them into your calculator, make sure you do exponents before you multiply, and then plot those data points on your graph. And just FYI, 1 times 10 to the 5th means there's 5 zeros. That means it's 100,000. So on my graph, those numbers on the side are 100,000, 200,000, 300,000, 400,000. Okay? All right, so go ahead and make your table of data and graph your function. Go ahead. All right, guys, so using my function here, if I plug a 0 in, so I put a 0 in here for t, what is 2 to the 0 power? 2 to the 0 power is 1, and then 1 times 10,000 is just 10,000, okay? If I plug a 1 in, 2 to the first power is, hello? 2 to the first power is 2 times 10,000 would give me 20,000, okay? If I plug a 2 in for t, 2 to the second power would be 4 times 10,000 would be 40,000. And then if I plug a 3 in, 2 to the third power, that's 2 times 2 times 2 is 8. So 8 times 10,000 is 80,000. And then 2 to the fourth power is 2 times 2 times 2 times 2. That's 16. And then 16 times 10,000 is 160,000. And then when we graph, we see it's a nice little exponential function. So 10,000 is going to be pretty low on here. For 20,000 is going to be pretty low as well. 40,000, I'm getting closer to that first tick mark. 80,000, and let's see, 160,000 would be up here. So if we continued it, we can see this exponential growth. It grows slowly in the beginning, and then it just kind of skyrockets up off of there. Okay, and that's characteristic of an exponential function. Okay, all right. So let's look at just a few more things Really quick here before I let you guys go with homework. So now using my function, this function that they gave us, 10,000 times 2 to the t. Calculate the house value in the year 2020. I know we've already predicted this, but now let's actually use our function. So 2020 is how many decades away from 1960? Six decades? Is that right? I think it's only 5, isn't it? 60, 70, 80, 90, 2000, 210, 220? 6 decades? Okay. So this year 2020 is telling me that t is 6. So I can easily do that, right? 10,000 times 2 to the 6th power. So 2 to the 6th power. Guys, let your calculator be your friend, okay? Some of these easier ones you're fine doing, but you'll see that we'll get to some where we have like decimals in the exponent and different things like that. Let your calculator be your friend, okay? So 2 to the 6th power gives me what? 64 times 10,000 would be 640,000, which is actually the same thing that we predicted earlier, right? Which makes sense. Okay, what if it gives me a harder question and asks me to calculate the value of the house in the year 2005? How many decades away is that? So we started at 60, 70, 80, 90, 2000, 2010. Oh, we can't go to 2010. So 4.5, right? So my t value then would be 4.5. So I could do a t value of 4.5 and then calculate 10,000. I'm not actually going to do it. Times 2 to the 4.5 power. That's really where your calculator is going to help you out. Okay? Okay, so do we have any questions? Okay.